All right, a little timer started, so we're good to go, and the doors are shut, sealing you in, no matter how boring I am. You can't leave. Hi, my name is Scott Gray. I am a senior architect, a senior technical staff member at IBM. I've been working for 3.5 plus so years on big SQL, and I'm now a lead architect for the open source group. And what this presentation is about, some of you may have possibly seen a presentation that I did with a colleague last year under the same title. And it was more about how we built big SQL. It wasn't a product pitch, it was kind of a technical pitch. But the topic really interested me. This is a nerd talk. It's the second of my nerd talks this week. And really it's not about any given product, it's not about any given feature. It's really to kind of teach you a little bit about how SQL processing on Hadoop works and why it works, and really actually more interestingly, why Hadoop is not a great architecture for the relational model. And that various products do backflips, jump through hoops to try to make this technology that's not so good at the relational model be good at the relational model. So, I try to be, well actually I've got some disclaimers, so I'll get to the disclaimers when I get to them. But this one's sort of an obligatory slide. I won't spend a lot of time on it, other than, why SQL on Hadoop? I think, why are you even asking? There's a million products out there. You're probably here because you're interested in SQL, and you're probably here because you know SQL. And so you want to exploit it. And traditionally, Hadoop has been a pretty difficult platform for developing against, unless you have some higher level language to make decisions for you. So we all know it, we all love it or have a love-hate relationship, but more importantly, there's a robust ecosystem of tools and there's a robust ecosystem of applications. Now, as far as SQL engines, there are 11 billion of them. All I had was this little stripe on the page here trying to fit some of the pictures, and I'm certain, I know I missed out on a bunch that I just simply couldn't fit in here. There are a lot of them. They have a lot of strengths and weaknesses. Several of them, like the only shameless plug I will have in here is for big SQL, is some of them have very, very rich SQL support. SQL 2011 support. In the case of big SQL, we have SQL PL support, which means we have stored procedures and functions and all of that good stuff that you've traditionally grown up with in a relational database platform. So when you put all this power of rich SQL in your hands, in the hands of Hadoop, all of a sudden you get this itch. You get this itch to suddenly, I've got this big expensive data warehouse, I've got this cheap platform made up of really interesting software with funny names. I would love to just do the data model plop. I'd love to just be able to take all that work I was doing, take my data model, pick it up, throw it on Hadoop on some SQL platform, take all the SQL that I was running, and voila, I've got my new data warehouse. And it sounds, it's really great. It sounds really promising. But hold on there, buckaroo. It's not quite that easy. Sometimes it might be. Certain data models are simplistic enough, some are denormalized enough that it may just work. But if you think about this, if you're migrating from Oracle to DB2, yes, I know you're all considering doing that right now. But if you were migrating from one data warehouse to another, you don't expect it to just work. They all have little idiosyncrasies. They've got features one does and one doesn't do. They have different ways of managing memory. So you need to spend a lot of time. You need to spend a lot of time planning and tuning and rinse and repeat until things are working pretty well. And now if you're taking your data model and just expecting to pick it up and plop it on Hadoop, you've got yet another series of challenges. It's also that you've got this platform that's just fundamentally different. It's fundamentally different from the sort of platform that you would run your SQL on a traditional system. I mean, just take the most basic case of mixed workload. Usually your enterprise data warehouse is on a dedicated set of boxes, and now you're sharing work with MapReduce jobs, that's dwindling, but now you've got your Spark jobs firing up, and everybody's using memory and CPU and network, and now how do you manage your work? So as I said, the world of Hadoop offers quite a few challenges to the world of SQL. But that's not to say, so I'm going to talk about places where Hadoop is really runs counter to the grain of the way you traditionally want things to work in SQL. But that's not to say that anything's wrong with Hadoop. Clearly it's not. But there's trade-offs. There's things that Hadoop's great at that have traditionally stumped the enterprise data warehouse, or certainly been difficult to do. And obviously it also opens up data well beyond just relational. So I could fill probably 4 hours, 5 hours of material easily talking about all these different topics, not just the challenges, but obviously I'm going to talk about some of the solutions here. Anything from data placement, challenges of doing indexing, DML, file formats, how do we deal with them, and so on. I've got a lot of possible topics. The ones I've got in blue are the ones I'm going to talk about now. If I had more time, and in fact, it's very possible, I never timed this, so it's very possible I'll run out of time, but that's okay. You'll have the slides, and it's supposed to be just kind of a fun topic to talk about anyway. But this isn't designed to scare you, to dishearten you, to make you throw up your hands and say, okay, we're not doing SQL. It's really just to make you think. Don't just go take your data model and plop it out on Hadoop and expect it to work, or well, expect it to work the way it used to. And also just to teach you, and it's also to kind of expose you a little bit to some of the technologies and tricks that are advancing every single day to solve some of these challenges. And as I said, I do work on one of these engines, so I work on it because it's a solvable problem. I wouldn't be building software that just couldn't succeed. And certainly we've proven it in a number of situations that we really can do some amazing stuff on Hadoop. And lastly, there's a lot of technologies. I don't know them all. I only know one or two deeply at all, and the rest I've been to these presentations and learned about them and then thrown up information on slides. So if I missed something that you really find you feel strongly about, I apologize. If I get something wrong, go ahead and call me out on it, because I'm learning too. So the first topic, and the one nearest and dearest to my heart, is one about data placement. So in a traditional data warehouse, data placement plays a key role. When you partition data, you would typically do things called co-location. So you take two tables and you would partition them, and you'd very explicitly say, this data, maybe it's for my employees, and maybe I partition by name, and I say, I'm going to take all the names from A to C, and note over here, you own that, and from D to F, you own that, and so on, and I partition all my data. And then I take all the tables that I'm likely to join to, and I partition them in exactly the same way. And this co-location of data allows a really nice optimization, which is now anytime I go to join those two tables together, I can get all my nodes working in parallel, because they've all got the same data on the same key, partitioned the same way. So I can do all my local joins there very cheaply, using all the available buffer pools and memories and all those exciting things. And then just take the result of all that joining and filtering, and then go to the next step of my SQL statement. Now, problem is, in the Hadoop world, we've got HDFS. HDFS is wonderful. It scales transparently and automatically, and you throw a new node and things get bigger and bigger. But it does that via random data placement. When I do a write, the blocks get randomly scattered across the cluster. Obviously, this makes a real big problem. The data for two tables, even if they were written from the same node, you can't really be sure the blocks are on the same machine. They can still be scattered somewhere randomly across the network. So what this means is I can't do co-located joins. And I'll put an asterisk. I'll talk about some of the either upcoming technologies or tricks that could potentially be played to get around this. But by and large, looking at the SQL solutions, SQL and Hadoop solutions out there, by and large, this is a problem that isn't solved. And what are the implications of this? How does a join work in Hadoop? Or more importantly, how does a join work when you don't have co-located data? That's really the way to state it. So I won't spend a whole lot of time with this, other than to say, there's two basic approaches. There's many little optimizations and tricks, and those of you that have heard Bloom filters is it's a fun little thing to talk about. There's all sorts of optimizations, but by and large, it boils down to this. If I got two tables and they're randomly scattered across my cluster, and I'm going to join them together. What happens is I get nodes working in parallel. Some are reading tables, the rows from T1 and filtering them, applying where clauses. Some are reading, other machines are reading the rows from T2 and filtering and applying where clauses. And then what they do to join the data is they'll pick another node, and they'll say, let's say I'm joining sales and, departments and employees. What they'll do is they'll say, and I'm joining by department, they'll say, okay, I'm going to pick one node on the cluster that's responsible for department 1. And each of those guys processing their data will ship the data for department 1 to that node. And now that one node will do the join. So now if you think about this, what actually happens in the absolute worst case, if I have a join with no where clause and no filters, and I'm not applying some of the little boom filter tricks, just doing a basic join, I could potentially move let's say I'm joining 2 petabyte tables, I potentially have to move 2 petabytes of data across the network. Or sorry, if I had 4 petabytes, I can do math, 4 petabytes worth of data could potentially move across the network. That's an expensive join. By the way, in your enterprise data warehouse, if you joined the 2 tables that were not partitioned on the same key, you've got the same problem. So this isn't specific to Hadoop. It's just something that HDFS kind of aggravates a little bit. And similarly, there's another trick called hash join, where you can move one of the tables, you copy it off to every node, they hash it into memory, and then they do a local join. So it's far more optimal, but I'm still stuck with moving one table or at least one filtered result off and copying it out to every one of my tens of thousands of nodes. So these are some of the approaches that you have to take to apply these sorts of joins. So that's kind of a problem statement. Now, in terms of solution, possible solutions, I'll start from sort of this. These are at least the first one. There are, from the HDFS perspective, there is kind of sort of support for pluggable placement policies, where you could conceivably say, any data in this given directory, here's the placement policy dictates that they must reside on these sets of nodes. So you can kind of force a co-location. But the problem is, of course, this is sort of an all or nothing, that you would end up having to state that the whole table must live on this node, or a partition must live on a given node. And more importantly, you've got the same problem. What happens when that node fills up? What do I do? Where do I put the data? And how can I deal with co-location? So I haven't really seen this used in the wild from a SQL, from a SQL engine. And again, if somebody knows of one, I'd like to learn about it, just to know. And then there's other things going on in the world of HBase. I'll intermix HBase in here, by the way, because a lot of the SQL and Hadoop solutions will federate to HBase. So they're treated just almost like a data source, like a file format, kind of, in the Hadoop world. So I'll bring HBase in and out of this discussion. But so in the HBase world, today, by and large, when you create a table on HBase, it's again kind of randomly partitioned, randomly scattered across the network, across the cluster in different region servers. But there is a mechanism, again, kind of a pluggable placement policy, where you could force 2 tables to always be partitioned the same and to split together. So you can actually force co-location with HBase. And I haven't today seen of the big names that most people know, like the ones I had on that second slide in. I haven't seen anybody using this, but certainly I've seen a lot of experiments and prototypes around it. And I think you'll start to see, it's kind of the ideal solution, because the tables can still split, they can still grow and span the network. But HBase and through this placement policy, you can always make sure that the co-partitioned tables always reside on the same nodes. And another trick that's played, and those of you, I'm sure many of you are familiar with Hive. I just thought I couldn't leave out the discussion of kind of Hive-style partitioning, which in the warehouse world, I don't know if you would call it partitioning. But what it really is so since I don't have a placement policy, what I can at least do is say that I am going to break my data up into groups. And in this case, I've got a table. I've said it's partitioned on state, which means really that I'm grouping my data by state. And what it physically turns into in Hive are subdirectories. So every state gets a subdirectory. And then what happens at query time is I run my select statement. It looks at my where predicates, and it figures, I don't need to read all the data, I just need these directories. which, actually it's a nice little trick. It works pretty well. It doesn't work well for joins. If you tried to use something like this for joins, in the vast majority of cases, even if you had two tables partitioned, if you had the one table was partitioned, the other one wasn't, you might have, if you tried to take advantage of it, for every row you read in the big table, you would have to go find the appropriate partition and scan the inner table, which would fall apart very quickly in terms of performance. And I will mention, so this is in Hive, I kind of call this value partitioning. For every unique value, you get a directory. There's other platforms like Jethro Data has range partitioning. There's other ways to do it, but they all boil down to kind of the same trick. Create a directory and put data in it, and then prune by directories or prune by chunks of data. Another solution, this one's more of it's not an industry solution, it's more of just an architectural, how do I get out of this whole problem? And it's a decision kind of you need to make as a data modeler, as a data architect, is you can just avoid the join altogether. And that is denormalize, kind of. Take advantage of the fact that many of these database platforms support complex data types or nested data types. So in the case of, on the far right here, I've got an example in Big SQL where what I've done is I've nested my department-employee relationship, where I've said for a given department, I'm going to have an array of employees, and I have all my employee information. And the data in this, again, just an example, I've got it stored as JSON. So as I'm reading my JSON, it's exploding it out into these data structures. And then if I want to do things like do a salary, what are the total salaries by department, I can use ANSI standard SQL to unnest all of this data. Other really interesting technologies out there is Apache Drill. A drill allows the same sort of exploration, the same sort of querying, just kind of with the added benefit that I didn't need to declare the table in advance at all. I just tell Drill it's a JSON table, and it begins exploring the data and doing its best to apply where predicates as it searches. And similarly on the Impala's got just kind of a slight twist on this, where they're kind of treating arrays of structs in particular as kind of first-class citizens and saying that anytime I have an array of struct, I can treat it just like a table. And that or if I have an array of numbers, I can apply an aggregate to it. So just some simple things are really just tweaks on SQL, but ways to make it easier to work with this sort of data than the strict ANSI SQL methods that are given to you. But this of course comes with a trade-off. So while you're avoiding the cost of these joins, which is great, your data is now bigger, depending on the storage format that you may have chosen for your data, you typically, when you read a row, you typically have to read the whole row. So even if you were just trying to look up, give me the count of departments, in the process of reading that department, I had to read all the employee information as well. So now suddenly you've made it quite a bit more expensive to look at a row. Not all storage formats, the columnar ones can be a little bit smarter about it. And then obviously the final one is you aren't relational anymore. Slicing and dicing data in this fashion, you can still do it, but it becomes more and more expensive to do it. So it's as with everything, it's a trade-off. So the next topic I wanted to talk about was indexing. So again, by and large, I think you don't see indexes that much in the wild in the Hadoop ecosystem. I guess a year or two ago, I would have said you almost never see them. They're beginning to spring up, and sometimes they spring up in a form that you don't immediately recognize as an index, and I'll point one of those out in just a little while. But indexing on Hadoop is a challenge, and again, it all boils down to this random data placement. So, the problem now is, in a traditional database, you would have, say, an index file, some kind of B tree, an index file, and a base data file. And when I go searching, I go walking down through my B tree, looking for the row or rows of interest, and then going over and looking at the data file, or looking at my cache of the data to go look up the row. But now, if these were just files on HDFS, where does a file live? Everywhere. The file's everywhere. So for a given block, for one block of my little orange blocks there are index blocks. For a given block of an index, I might be scanning through that index, and now I want to go read the row from the base table. Where does that row live? Somewhere out there. On some block, on some node, somewhere. So I might need a network hop to go open that block, seek to the appropriate location, and read the base row. So the traditional way of doing indexes is pretty challenging on the Hadoop side of things. And so obviously, if you were to do a scan of a huge range of data on the index, it might be a network storm trying to go access all this base table data. And also, the last thing I know from from big SQL is most of the SQL engines out there don't own the data. They are simply kind of an engine running on top of the data. So you get the one little additional burden that we always have to deal with is somebody goes and throws new data on the file system behind the scenes. Is it indexed? No, because we didn't know. We didn't know it was put there. So anyway, you have this problem of synchronization of the index with the base data in this case. I debated putting this slide in here because it's really esoteric and nitpicky, but it's kind of interesting because it also leads into the next slide. Because coming from the big SQL world, we always get, big SQL integrates with Hive, and so people say, what about Hive indexes? Why aren't you using Hive indexes? Well, I'm going to describe to you why not. But I have to give you a little tutorial first, which is about, so those of you that have worked with Hive, Hive can work with almost any data style of data, and it does this by working with some standard Hadoop classes called input format and output format. These are, the input format's responsible for interpreting the structure of the file. It's responsible for figuring out how do I partition it, how do I split it, so that I can put many workers to work reading it. And the interfaces are great, and they're ubiquitous because they've been there forever. And so as a result, Hive can access just about any type of data you can possibly imagine. But the architects miss something. They have no seek operation. You can open, you can get a partition, and you can read from beginning to end a given block, a given segment of your data, but you can't seek. And the problem is when you have an index, and the index says, this row begins at, the row in the base data begins at byte 43 billion. I can't seek to 43 billion. I can maybe get to the block and read the block from beginning to end, but I can't seek. So what that shows itself as are in the world of Hive indexes is they have this concept of an index, but because they sit on top of these Hadoop classes that have this limitation of seek, then so the best they could do is that they say for whatever I indexed, in this case I've indexed, I called them column A and B, but it's state and town. So for a given state and town combination, they'll record what block, because I can kind of grab a split and look, I can look at a block and they say what block did that data live? And then what they do is they store a list of bits, and that is basically every row in the block. They have a 1 if there's a row that matches, that has those two values, and a 0 if it doesn't. And so it's actually relatively useful, especially if the data was sorted. You can quickly discard blocks trying to get to the data. Say if you just wanted to look at California or just California and San Jose, you can quickly discard blocks to get to the one that's interesting. But once you're at the block, you still have to read it beginning to end. And so you look at the ones and zeros to figure out if the row is interesting or not. But this is the part that excited me when these things started to pop on the scene. So indexing is a challenge, no doubt. And I mentioned the problem of synchronization. How do I keep the index synchronized with the base data? You've got this globalization but what if we inverted this idea of how an index should work, and instead, and by the way, this isn't unique. Products like Netezza have been doing this for some time. But what if we embedded in the data, in every block of data, we had a little mini index? And not just index, but we had a mini index, and we had statistics about what's in the block. And so we have all this metadata about the data in the block. Well, that's what these new file formats like Parquet and ORC are doing. So typically, they've got their data compressed, so it's stored very efficiently. They have this indexing and statistical information, and more importantly, when you go to read from them, again, you'd only know this if you worked at the API level with them, but when you go to read from them, you give them search criteria. And you say, here's what I'm interested in. And then what they'll begin to do is they'll begin to go to block by block by block and say, does this one have any relevant information? And if so, maybe where is it in the block? But with the, actually we were just having, I missed the presentation, but they were talking about the latest enhancements to ORC. And with some of the tricks that they play, they can actually fetch a single row out of billions in a second by very quickly, again, the data has to be kind of optimal for the metadata they track, but by quickly blasting through all the blocks, and blocks are big, so if I can discard a block, a 256 megabyte block, I just discarded a lot of potential work. So if I can blast through and start discarding blocks, I can very quickly find my data. So a really fascinating topic, and I think is a really elegant solution to some of the indexing problems that are out there. But you still do at least have to look at every block, which means I have to open it, peek at it, and move on. And the last piece of indexing that I'll talk about is, again, I'm going to jump back to the fact that HBase is frequently used as a SQL a storage engine for SQL access. So is indexing in HBase. So HBase is inherently indexed. It's built into it. Every table has a row key. Every row key is effectively indexed. I can go fetch a single row very, very quickly. Now the trade-off for that, of course, is writes. Writes into HBase are dramatically slower than, say, just writing to a file. And also, I didn't mention it here, but scans in HBase. To go read a table from beginning to end usually is 2 to 3 times slower than scanning data just raw out on the file system. And lastly, in order to maintain this index, it needs all this infrastructure. It has servers out there, they're caching stuff in memory, they're constantly reworking pages and rebuilding indexes, and so you're consuming a lot of resources, but for good reason. It provides a lot of functionality. So in a way, you get a free index on every table you put in HBase. And I can tell you with Big SQL, we take great advantage of that. If you fetch a row, we go straight to the row. If you fetch a range of rows that are part of the index, the primary key or the key of the table, we find it very, very quickly. But traditionally, HBase hasn't had any a native concept of secondary indexes. But there's some open JIRAs around actually adding support within HBase. However, that doesn't mean you can't do it. Many of the SQL solutions out there, Big SQL included, provide support for secondary indexes. So typically all a secondary index is just another HBase table. So in this case, I've got my table T1, I've created an index on columns C2 and C3, and then what all these, the vast majority of these solutions do is they just create another table out there, they make the row key the values of C2 and C3, and then they store the row key of the base table to point back so you can go find where the row or the matching rows are in the base table. All of these solutions that I'm aware of maintain these indexes. HBase has this thing called a coprocessor. It acts sort of like a trigger in traditional SQL. So if I put a row in the base table, it will automatically go update the index. If I delete a row in the base table, it'll delete it from the index. But I'll mention, typically these suffer from the problem if you try to bulk load the table, the coprocessors don't run. That's just kind of a note. And other solutions, Big SQL is one of them, are beginning to look at maybe storing the index outside of HBase, but again, managing it with a coprocessor. In addition, there's another interesting problem with index, or a potential problem, but there's a possible solution with trade-offs of indexes in HBase. And it kind of goes back to that same HDFS placement problem. So when I create a table in HBase and I begin writing data to it, at first the table starts off generally on a random node. It fills up, it gets too big, it gets split, and the other part goes off onto some other random node. So now if I have my index, like I described it, it's just in another table. Remember, it's growing, it's splitting, but it's growing and splitting on other random nodes. So it's still this global index problem where the data in my index is pointing to rows in my base table, but those rows in the base table may be on a different node. But does that mean the index is useless? Absolutely not. You know, if you want to fetch a single row, it may require going to look at the index and then going to look at the, you know, 2 quick network hops, but I still can get my data in a fraction of a second versus the time it would take to scan the billions and billions of rows in the whole table. So it's still, and even for, you know, smaller scan ranges works great. But, you know, as soon as you start scanning really big ranges of data, through your index, maybe you're gonna begin to have a trade-off between maybe it would have been cheaper to go just do a table scan on the base table. And a good cost-based optimizer, like in Big SQL, I told you I wasn't gonna plug it, but I'm still doing it. So a good cost-based optimizer will help make that decision for you. You know, where's the trade-off, what's the crossover, and when should I just do my table scan? However, you know, that doesn't, not all is lost. HBase does have a mechanism where you can control the placement. You can control how when it comes time to split a table, you can control how and where it splits. So Phoenix currently takes advantage of this. Phoenix will do both of these, both a global and local index, where it will make sure that the index table is indexing the data only for the based data on the same node. So that seems like, you know, at a glance, it seems like it completely solves the indexing problem. But, you know, if you think about what happens now, so in the case of the global index, if I needed to look up one row, I might have to go to one node to find it and one node to go find the base row. But now, if I want to find one row with a local index, how do I do it? I actually have to go ask every node. I have to ask every node's index, do you have a match? And then if you do, I go back to that node and say, now give me, you know, or a coprocessor can do it, but now go give me the base data row. So I have to ask more nodes. So again, it's a trade-off on which one you choose. So the last topic that I'm going to cover here is DML, data manipulation. So the other interesting aspect of HDFS, because it was built, well, it's not POSIX compliant, but it was deliberately done so because it's built for large-scale analytics, is it has no update. You can open a file, you can append to a file, you can delete a file, but I can't just seek somewhere and start writing. It doesn't support that, and which makes things like update pretty difficult. I will mention, when I was kind of researching as I was putting this presentation together, I ran across this JIRA about variable block length and block append. This is completely nerdy. Many of you may not care, but I did notice. So they're adding the ability, or have added it for 2.7, where the blocks don't have to be the same length, and I can open a block and begin appending to the block. So I can kind of grow my file, and I can add new data in the middle of my file. And looking under the hood with 1 or 2 small tweaks, I think you could get a crude update mechanism. You could have a crude ability to slice data out of the middle of a file, or to add data into the middle of a file. So I think new tricks will be played soon. But so as a result of this non-updatability, you'll notice there aren't too many solutions out there. There's a few, and they're growing a little bit, but you'll notice not too many of them do data manipulation. You can do inserts and appends, but no updates or deletes. And those that do support it, HBase is one of them. Hive in 0.14, I don't know if any of you saw Alan Gates' presentation about Hive acid table support. So some of them do have support for it, but they have to bend over backwards to do it, and it's definitely not without a cost. And they all take a very similar approach. So I'm going to talk a little bit about how Hive does this. I blatantly stole the diagram from Alan Gates' presentation. Thank you, Alan. But they almost all take this same sort of trick. So what Hive added was this ability, though they call it acid, they're getting acid compliance is, you know, atomicity. Anyway, the ability to have transactions. They today don't actually have the transactions spanning tables. They will, but I won't nitpick right there. That's not the point. But so most solutions take the same general approach. You write out your base data. You've got this big file full of data now. Now along comes an update and delete, update and or delete. So as you're reading through the base data and you find a matching row and you apply the operation, what that apply actually means is I can't change the original data, so I'm going to create a log, effectively, they call it a delta file, containing a log of the nature of the changes that happen to the base data. And I'm going to write it out effectively right next to the original table. And every time someone does another update delete, they just create another log. Now, these logs are stored in row order, and they keep track of which row from the base data was changed. So what happens now at read, when I go to read the table, is you open the original table, and you open all the delta files, and you begin reading. And you begin looking at the first row of every delta file and if you find a match, then instead of returning the row that was in the base data, you return the row with the operation or operations applied. Well, you apply the operations in memory and then ship the row back. It's a simple trick. Most databases, many things work this way, but it's a nice trick that works. But one thing you'll notice, it's not really suitable for OLTP. It's big bulk batch operations. You would like to keep these delta files. You don't want to go update one row because you'll end up with a delta file of one row. If I update a billion rows that way, I'll have a billion files. Well, it does compaction and things to patch things up over time. And they got processes behind the scenes to begin rebuilding. They combine these delta files together, and then over time, they may even go rebuild the base data. But it's a big involved process. And now, actually, I'll do this quickly because I'm about to run out of time, but this is the last slide on this topic. So the last piece is just data modifications, and how does HBase do it? So HBase very, very efficiently allows for update or actually upsert, but update and delete semantics. And really, they're doing the same thing. They're keeping a log of the data. They're keeping a log of the data. They're periodically reapplying the changes in that log and rebuilding the beta data in the base files. The only thing is they can get away with making it fast by having a server, by having something out there that's holding the state in memory. That's when you go to ask for a row, it might have the delta of the changes that occurred in memory, and then when it's time to flush, they go rebuild the original base data. So that's really how they pull off the performance, but they're doing the same trick. And the last bullet was just something from the big SQL side of things that we discovered, or not discovered, but we've been looking very carefully at. Is that HBase actually supports this thing. Its updates aren't really updates in the traditional SQL sense. They're upserts. You kind of insert a row, and if another one already existed, it gets replaced. If it didn't exist, then you insert the row. And anyway, it's an esoteric topic, but it's actually kind of difficult to implement, or at least costly to implement a pure SQL update statement. So anyway, I don't know if this was interesting or if it was boring. It was interesting to me because I got to learn all this with Big SQL. But there's a lot more challenges that we had to tackle when we built Big SQL. There's a lot more challenges that other products are having to tackle as well, from having to deal with the plethora of file formats that are out there versus some might pick one single file format and you optimize on that file format. Great for performance, not so great for being able to share across the ecosystem. There's all sorts of challenges around caching with different compression algorithms, with different file formats, and mixed workload. Caching's a real challenge. Schemaless, the fact that a lot of data, depending on the file format, doesn't really have a schema in advance, it can pose a real challenge to SQL, and that's where projects like Drill and Dremel came out of. Optimization and data ownership. If you don't own the data, if someone's just throwing files out there, and how do you optimize if you didn't have statistics built in advance? And there's really interesting, clever things from dynamically learning about the structure of the data as a query runs. Anyway, there's lots of interesting things that would be fun to talk about. Security, when you don't own the data again and you want people to be able to access it from SQL and from other tools, there's huge challenges in the world of security. And then I mentioned the one at the very beginning about competing workloads. Now, when your relational database engine doesn't run in isolation, what do you do? How do you deal with it? Yarn helps this quite a bit, but it doesn't quite fully solve the problem. They're getting there. They're headed in some positive directions, but it still is a real challenge in the relational world. And that is it. And actually, I used every last minute. But maybe, I don't know, if you need to leave, go ahead, or we could ask questions, or I could stand down here if you want to just come ask a question. Yeah?
The question is based on your detailed understanding of all the various file formats and the challenges with interacting with those file formats, what do you see on the horizon for transactional happening? What kind of OLTP solution?
Yeah, so the question was, what's on the horizon for OLTP on Hadoop? Well, I think that's an interesting question. I mean, you've got Splice Machine out there, and really most of the ones that I see out there are kind of on the order of Splice Machine, where you've got something like HBase, which has all the fundamental underpinnings for doing, for being able to at least quickly do changes. Then you've got projects on HBase that allow for actual transactions. And so I think I see the world of HBase beginning to incorporate some of those. And I think once HBase settles on a single transaction mechanism, if it does, I think you'll start to see more and more of the SQL solutions taking advantage of it. Any other questions? Okay, well, if there are, I'll be here. But thank you very much.